I've wired a parallel circuit here. All the electrons travel from 119. We're using this random spring right here just as a connection point to be able to get another wire in here since the wire wasn't long enough. We come in with our current at 79, and instead of having to go through the resistor to 80 and then jump a wire from 80 to 81, we're putting a branch in. The electrons could flow down this wire, and they could either go through the 4.7 k ohm resistor here, or they could go through this loop of wire and go through the 10 k ohm resistor. 80 and 82 are connected together by this second orange loop here. So any electrons that opt to go through the 4.7 go through that wire and catch up with the blue wire to head back to complete the circuit. The electrons that flow through the second branch and go through the 10 k ohm resistor also are able to travel through the blue wire and complete the circuit. This is a very simple parallel circuit. These two resistors are said to be in parallel with one another. Let's find out what's going on with voltage and current in this parallel circuit. I'm set up with my 3¼ volts that I had in my other circuits, and my two resistors are in parallel, and I'm going to measure the voltage across the first resistor. How much voltage is that dropping? When I introduce the meter, what we see is 3¼ Well, wait a minute. The battery was 3¼ How is that resistor getting 3¼ And in my parallel circuit, when I move the probes to measure the voltage across the 10 k ohm resistor, in other words, how much voltage is that dropping? Now the first one dropped 3¼ which is the same as the power supply. So what's going to happen here with this one? It's going to be 0, or is it going to be? Well, it turns out that's 3¼ also, which introduces us to an interesting thing in parallel circuits. The voltage drop across the parallel components will be the same, or be constant. So 3.24 volts is available coming in on terminal 79, and so each of these two components equally drops the same voltage drop. Interesting. This time in my parallel circuit with these two resistors, I've reconfigured it a little bit. I want the electrons to be able to flow from the battery on this blue wire and be able to go to the second branch, which is this 10 k ohm resistor. But if the electrons are going to take the first branch and go through this 4.7 k ohm resistor, I want them to go through the meter first, and I want to measure the current. Now I've set my meter up to measure current, and I put the dial on before I made any connectors, and I'm set on probably a range that's not sensitive enough because I'm showing 0 amps. So if I click this one notch down and go to 200 milliamps as the maximum range, that increases the sensitivity. I'm able to detect 0.6 milliamps is traveling through that first resistor. So what will the current be in the second resistor? So I've reconfigured the parallel circuit now so the electrons can travel through this wire, and if they go on the orange wire, they're going to flow through the 4.7 k ohm resistor. If they flow through the red wire, they'll go to the meter and come back and flow through the 10 k ohm resistor. So we'll be able to measure the current in the 10 k that goes through the 10 k ohm resistor. In the 4.7, it was what? 0.6 milliamps. So what do we get when we measure the current through the 10K resistor? 0.2 milliamps. Interesting. What could be happening here? In this configuration of the parallel circuit, what I've done is all the electrons travel through this blue wire, and all the electrons are going to travel through this red wire to the meter probes, go through the meter and come back through the black. And then all of the electrons will then be able to branch. Some will go through the 4.7K and some will go through the 10K. And then all the electrons travel on this blue wire back to the power supply. We'd already previously measured 0.2 milliamps in the 4.7K resistor, and we've measured 0.6 amps, 0.6 milliamps through the 10K ohm resistor. So what's the current going to be through the whole circuit? 0.9 milliamps. Well, there's a slight bit of error in here. 2 and 6 should equal 8, and we've got 9. So evidently the 0.2 milliamp reading may have been slightly higher than 0.2, and similarly the 0.6 milliamp reading could have been slightly higher than 0.6, and that would account for the slight discrepancy. Brings us to another principle. Components hooked in parallel will have the same voltage drop, but their current consumption will be different. And in fact, the lower the resistor value, the higher the current consumption. The 4.7K ohm resistor used 0.6 milliamps. The smaller resistor used more current. The bigger resistor used less current at 0.2 milliamps. How does that make sense? Well, electrons will travel in the path of least resistance, and it's easier for the electrons to travel through this resistor, so more of them will travel through the lower resistor, 0.6 milliamps in this case, and fewer electrons will travel through the more difficult resistor. Now, why don't they all just go through here? Well, an interesting phenomenon is it is mathematically predetermined how many will go through each branch, and we can use Ohm's law for that.